Alright, so here's a second video where we're going to review logarithmic function. In the first video we reviewed exponential function. Okay, so here we go again. This is the graph of an exponential function. You know, this is a graph for which the base is above 1, the function is increasing, and I put the 2 points we usually plot on such a graph. Okay, well, this function obviously passes the horizontal line test. Okay, another way of expressing that, well, if it passes the horizontal line test, that means the function is 1 to 1. That means it has an inverse. Let me write it. Okay, so y equals a of x passes HLT, the horizontal line test. That means, so y equals a of x, this function is 1 to 1, and that means that it has an inverse. Y equals a of x has an inverse. Y equals a of x has an inverse. Okay, that's what it means. Let's quickly review this concept right here of a one-to-one function. What does it mean? It means, of course, if you have an equality of input, okay, if two inputs are equal, then the outputs are equal. Well, that's really nothing new here. That's just the characteristic of a function. Okay, characteristic of a function, not of a one-to-one function. Okay, equality of input implies equality of output. That's just a function. All right, if you don't have that, you don't have a function. It doesn't pass the vertical line test. This is about the vertical line test. Well, the horizontal line test is the other way around. If you have an equality of outputs, then it implies an equality of input. Now, this is a much stronger requirement. This is a one-to-one function, one-to-one function. Okay, so I'm assuming I'm dealing with a function. Okay, I'm assuming this is a function. Okay, output of a function, and it's a one-to-one function, and this is graphically, this is characterized by the horizontal line test. Okay, so this is what it means to be a one-to-one function, and you know that such functions have inverses. Okay, all right, so you remember how to draw the graph of an inverse function, right? Here, let's recall the geometrical property of the graph. Well, this is not good enough. The geometrical property between the graph of a function and the graph of its inverse is that there are symmetrical respect to the line y equals x. This is the line y equals x. Okay, y equals x. And the graph has symmetrical respect to the graph. What does that mean, symmetrical? That means you have to go right on the other side and perpendicular to the line and same distance on both sides. Here you're going to find this point right here, and here you're going to find that point right here. Okay, well, I'm kind of cheating a little bit here because I know I should be right here. Anyway, here we go. And the horizontal asymptotes of exponential will become vertical asymptotes of logarithm, right? So the inverse of exponential base a is called logarithm base a. Okay, by definition these two functions are inverse of each other. So look, let's we only wrote two things about exponential, actually more than two. We also noticed some limits, but we wrote the domain and range and then some limit stuff. So you see the domain of an exponential is all real number, and the range is positive real number here, actually. Let me rewrite that right here. Okay, so I'm going to use a notation I've used in class. Okay, very briefly. I don't want to linger on this notation, but it's kind of nice just to write the function. This is exponential base a. We said the domain is all real number, and it goes into, do you remember the notation for a function? The range is positive real number. Well, guess what? The log base a will switch everything, right? The log base a will start there in the range of the exponential, and it will go into the domain of the exponential. That's a domain of log, and that's a range of log. Okay, you switch domain and range when you I'm sorry, I meant range. You switch domain and range, you flip them when you deal with a function and its inverse, okay? I'm not going to write limits. Okay, all right. So let's write now the characteristic property between the graph of a log and the graph of its inverse, okay? Before I do that, what you doing here? Before I do that, let's recall the property that properties between y equals f of x and y equals f inverse of x. Let's recall the geometrical property. We've recalled it, symmetrical respect to the y equals x line. That's a geometrical property. The analytical property, well, let's recall them, okay? So the first one is that f brings x to y if and only if f inverse brings y to x, okay? If you think in terms of carrying, bringing, it's easy to remember. Number two, second property. If you take an input and you put it in f, and if this output right here, it's an output of f, you put that into f minus 1, you're gonna land exactly where you started. And property number 3 is the same one, but you start with f minus 1, okay? Input into f minus 1 and you throw that into f, you're gonna land where you started, okay? Well, what happens to this property now when you deal with logarithm and exponential functions? So I'm just gonna rewrite that, that's it, okay? But instead of being called property, now it's gonna be properties between exponential and logs. Exponentials and logs, okay? All right, let's write the first one. So what does it say, the first one? It says that if you take an x and you put it into an exponential function and it goes to y, okay, if an exponential function carries x to y, then actually it's not if then, it's if and only if. If and only if the log, the inverse of exponential base a is a log base a, the log base a will carry y into x, okay? Second property, if you take an exponential function, if you take a value, an input, and you put it into an exponential function, and if this now you plug into a logarithmic function, then you'll be back to where you started. Property number 3, if you take an input, you plug it into a logarithmic function base a, and this now you plug into an exponential function base a, then you'll be back to where you started, okay? We went over that in class, that's why I'm going a little bit fast, all right? Okay, you know what I'm gonna do actually right now? I'm gonna rewrite these 3 properties for the 2 most common log, so you know the 2 most common log, okay? Let's rewrite that when the base is e, and let's rewrite that when the base is 10. Base e, this is called the natural log, okay? Also called Neperian log. I'm not sure how to spell Neperian. It's with maybe with an a. Neperian log. It's from the dude who studied log, and this is called the decimal log. Decimal log. Very common in science, so this is for science usually. Well, this right here is for math, okay? And actually, if you're in math, you always deal with a base e. Reasons, well, there's some reasons for that. I'm not gonna go over that right now. Okay, so what happens to the first property? Well, hey, the first one right here says that if log ln carries x to y, then that's a no, sorry, I start with exponential, right? So if the exponential base e carries x to y, then that's the same as, now log base e, you know we write that ln, right? Ln log base e carries y to x. Second property, if you have an exponential base e and you put that into a log base e, you just find x. Third property, if you take an input and you put it in a log base e and you throw that into the exponential base e, you find x, okay? All right? And on this side right here, Let me rewrite the same property with, did I put 1, 2, 3? Yes, I did. The same property with base 10. So 10 to the x equals y if and only if log of y equals x. See, I do not put the base, that means base 10. Number two, you take an exponential and you plug it into the log with the same base, okay? It doesn't work if you don't have the same base. And number three, you take 10 to the power of a log base 10 of x, and that again is just x, okay? So here are the properties of log and exponential. I'm gonna stop this video right here. I have a couple of properties of log to cover, but I'm gonna keep that for the last video, okay? Short video.